In this video, we're going to use LT-Spice to simulate a very simple circuit involving a diode and hopefully plot the resulting diode characteristic. LT-Spice is free software and it's available for both Windows and Mac. In this particular video, we're using the Mac version of LT-Spice, though we'll be producing a similar version for Windows as well. The reason I wanted to do a Mac version specifically is because when we first open LT-Spice on Mac, it can be a little bit daunting in the sense that when we've just opened a new schematic like I've just done here, we're presented with a blank screen and there's not very much in the way of toolbars or buttons or controls. And the reason being that on the Mac version these controls are still present, but they're a little bit more hidden than they are on the Windows version. So if you have a look at the equivalent Windows version of this video, you'll see that the interface is a little bit more user-friendly. There's more controls and toolbars and that kind of thing. But the underlying software is still the same. We can still do all of the things in the Windows version that we can in the Mac version. And it's just a little bit more awkward to get the hang of to begin with. What I recommend doing is familiarizing ourselves first of all with the function keys. And when I mean the function keys, I'm talking about the F1, F2, F3, F4 going along the top of the Mac's keyboard. But when we type a function such as F1 on the Mac, we have to hold down the function key first, which is in the bottom left-hand corner of the screen. So you'll see the FN function key. So FN F1 would be our first function key. We hold down FN and then press F1. And the same thing for F2, F3, F4, F5. I only mention this because I'll refer to commands like F1, F2, F3, but we know now we need to hold down that FN key first of all. So firstly, I want to use the command F2, the function key F2, because F2 opens up this window here where we can insert components. And we're going to just insert 3 components to begin with. The first one is a voltage source. So I click on OK, and I can place that anywhere. It'll keep that voltage source on my cursor to place more voltage sources. I just escape that by pressing escape, and that'll disappear. FN F2 again, and we can insert a resistor. And resistor is just listed as res. When I'm placing a component, you'll see at the top of the screen there, I can rotate it. We can press Control and R to rotate and then place it. Again, we'll press Escape. And the last component we're going to include here is a diode. So F2 again, and we'll find diode. We're just going to use the generic built-in diode in this software, but it does allow you to pick different diode models and manufacturers and that kind of thing, but we're just going to use this generic diode to begin with. And then again, press Escape to exit that. One thing to mention at this point is we can move components with another function, which is the F7 key. So if we press F7, you'll see the cursor changes to a little hand, and we can then pick up and drag around components and place them again. That little hand remains to move components. I need to press Escape to get back to the normal cursor again. So if you do want to move components, you can use that F7 function. And if you want to rotate components, you have to have picked them up with that F7 function first. I'll give you an idea of what I mean. So F7 to move a component. Now that I've got it in my hand, as it were, I can then Control R to rotate it and then place again. So I'll press Escape. We've placed all of our components now. The next step is to join them up with wires, and the function for that is F3. So FN followed by F3 to place a wire. And I just click once where I want the wire to begin. I click once again for a corner, and click again where I want the wire to terminate. And we'll do the same along the bottom to connect our circuit. I'll press Escape to exit that as well. The last thing we need here is ground, and so we just press the letter G for ground, and there it is. And we'll place that along the bottom of our circuit. Again, I'm going to use F3 to connect that to my circuit there. So when we're measuring voltages, we're measuring them relative to ground. We'll see that apparent in just a second. What I'll do, just for the time being though, I'll insert some text. You can do the same by pressing T. And I'll just make a note of the functions that we've looked at so far. So we've got F2 to insert components. And we've got F3 for a wire, and we've got F7 to move components, and the last one is one that we haven't mentioned yet. It's F5, which we can use to delete components. So I'll give an example. If I press function F5, I could delete that ground there, for example. Just clicking once to delete. Now, notice my cursor is still on the delete mode. Don't accidentally delete things that you don't want to. I need to press escape again to leave that mode. I'll put that back in again, G for ground, and put that in there. Okay, so now we've got our circuit set up here, and we're going to perform a particular type of analysis on this circuit, which is a voltage sweep. We are going to, rather than have a fixed value for our power supply, we're going to observe how this circuit behaves when we try a range of voltages. And so what I'm going to do here is I'm going to add a command, a spice directive, by pressing the S key. And that opens up this, this dialog box here. Now again, on the Mac version, it's very hidden. If you're familiar with spice and spice commands, you can type directly into this box here, but hidden very sneakily away, if you right click on that box, there's this help me edit option, and in here analysis command, and we're going to choose that. It's going to help us to write our spice directive correctly. The type of directive that we want is a DC sweep, and we're going to set the name of our first source to sweep. Well, the only source that we've got in our circuit is V1. You can't see it underneath this dialog box, but it was called V1. If you've put several voltage sources in, or if yours is called something different, then whatever it's called in there, but ours is V1. Our sweep is going to be linear, and we're going to start at 0 volts. We're going to go all the way to 5 volts, and we're going to go up in increments of, let's say, 0.1 volt each time. So this analysis is telling the software to range our supply voltage V1 from 0 gradually all the way up to 5 volts in steps of 0.1 volts. And there you'll see it's typed out our spice command there. And so when I click OK, I get this text now in the box, and OK again. I can place this text anywhere on my schematic. It doesn't really matter where. Just while I remember, there we go, our voltage source name is called V1. Last thing I need to do, I'm going to give this resistance a value here. It needs to be given a value if the simulation is going to work correctly. Let's say that this resistance is going to have, this resistor is going to have a resistance of 1K, or 1,000 ohms. So there's our resistance value there as well. So now everything is in place. We've constructed our circuit, we've specified the type of analysis that we want to carry out. Now we need to run our simulation. So in the very top left corner, there's our little run icon. We click on that and we get this blank graph here, which at first glance isn't really much use, but we're going to sort that out in just a second. One thing that I want to point out though is notice that our x-axis going along the bottom of this graph goes from 0 to 5 volts. So that's our analysis working correctly, at least. We're measuring the voltage V1 ranging from 0 all the way up to 5. But at the minute there's nothing plotted. And the reason being we have to go back to our simulation. I've got it in full screen mode, so a 3-finger swipe will take us back to our simulation if you've got a trackpad or a similar swipe on the Apple mouse. And here is our circuit again, but notice if we hover our cursor over components and wires, we have some different cursors that appear. The first one of which is when we hover over a component, we get this arrow here representing a current meter. We can plot current, and so we could choose to plot the currents in different circuit components. Because this is a series circuit, I would expect all of the currents to be the same, but if you've got a more complicated circuit, you can plot whichever current is relevant. And then by hovering over wires or connections, or otherwise known as nodes, we can plot voltages at those particular points, and that's given by this little probe sort of cursor. And remember, we've inserted a ground here, so all of our measurements are relative to ground, and we'll be taking some voltage measurements as well. So firstly, what I want to do is I want to plot current. And what I want you to notice here is just a little idiosyncrasy of LT Spice. If you look at the direction of that arrow, it's plotting the or reading the current as going from right to left. And that's fine, but what happens is when we just click once there, it looks like nothing's happened, but when we go back to our graph now, we've now got a trace on our graph, but it's negative. And this is a strange quirk of LT Spice. We know that conventional current, positive to negative, should be flowing this way, but for some reason it's pointing right to left. Now there's two ways we can remedy this. The first way is to go back to our graph here, and when we hover over the title of the trace that we're interested in here, in this case it's IR1, the current through R1, you'll see in the description above there, we can command left click to reverse the cross probe R1. That's at the very end of that top line there. So we can reverse the probe because by default it's the wrong way around by the looks of it. The other silly way that we can remedy this problem is that we can simply rotate our component through 180 degrees. So if I do what we did before, where we command F7 to pick up a component, I just click once to pick it up, and then Control R to rotate it through 180 degrees. I put it back. Now, because it's a resistor, a passive component, that shouldn't make any difference to our circuit, and it doesn't, but it does make a difference to our analysis for some reason. When we press run on the schematic now, you can see that this is now a positive trace, and the current is pointing the right way on the diagram. So that's just a quirk of LT Spice, really. It is bothered for some reason as to the orientation of the resistor, but don't be thrown by that. If you start getting negative currents, you can simply use either one of those two methods to remedy it again. Anyway, let's go back to our graph here, because what we can do is a few different things with our current plot here. We'll notice that because of the semiconducting nature of our diode, that nothing very much happens current-wise for the first sort of 0.6, 0.7 volts of supply, and then gradually we see this increase in current, and that increases steadily, as we'd expect, as the supply voltage gets bigger. One thing we can do is, if we go to the top here to the title and just click once on the title there, we get a cursor. And we can take some very accurate readings by moving, just dragging that cursor. We have our horizontal scale, which is our supply voltage, and we have our vertical scale, which is the current. And so we could move our cursor to respective voltages or currents to work out corresponding points on the graph here if we want to get some accurate values. Another thing we can do, I'll just close that, is if we want to zoom in, let's say this corner here on the graph at around 0.6 volts, I can drag a box and we can get a much more accurate set of readings here. Notice the slightly sort of awkward straight line graph that's produced, these straight line segments that are joined together. That's due to the increments that we set. Remember, we set it going up in 0.1 volt increments. If we want a smoother curve, we could go back and change that analysis and rerun the simulation again. But at the minute, it's fine the way it is. We'll right click and then zoom to fit, and we're back to the full graph again. A couple of other things we can do here. If we go back to our schematic, we hovered our cursor over the resistor there to plot the current flowing through that resistor. But if we hold down the command button, we can also, you'll see the cursor's changed there to a thermometer. We can plot the power that's dissipated in that resistor. And if we click again, it looks like nothing's happened, but back to our schematic here, we've got another curve here, which is for the power. And you'll see here, it's not called the power, it's the voltage across that component, across the resistor. The voltage is expressed in the nodes V N001 to N002. So if I just go back very quickly and hover over here, you'll see at the top of the screen V N001, V N002. It's that voltage there, or that potential difference from node 1 to node 2, which is the voltage across our resistor, multiplied by the current going through that resistor. And we know that voltage multiplied by current is power. So we're seeing a power curve here. And we also get another set of axes down the right-hand side, which is measured in milliwatts, as opposed to our current down the left-hand side, which was measured in milliamps. So we now have two sets of y-axes to take both current and power measurements. I can do the same as before. I click once here, I can get a cursor for my power dissipated at different voltages. So here, for instance, at 2.5 volts, we're dissipating this much power. And close that again and go back to our schematic. So what I want to do for this last little segment is we've seen how this circuit behaves, or how we can produce a trace, a graph for how this circuit behaves as we gradually start to increase the supply voltage. But rather than the supply voltage, we're interested in the diode characteristic. And to do that, I want to plot the voltage across the diode, just the voltage across the diode, against the current through the circuit. Now the current part we're happy with, because we're taking this current here, which is not the current through the diode, it's the current through the resistor, but this is a series circuit, and so we know by the nature of series circuits that the current is equal all the way around, and so this current here through R1 is also the same as the current going through D1. I'm not too bothered about that, but the voltage here is the voltage that's supplied to two components. It's the resistor and the diode in series. I'm only interested in the voltage across the diode. And so how do we alter our graph so that we're just plotting what's called the VI characteristic for the diode only? Well, the answer is to do with those nodes that we mentioned before. We want to measure this voltage here across the diode relative to ground. And so the node that I'm interested in is this one here. And it happens to be VN002. It says at the top of the screen there. And so what I can do is, by plotting VN002 on my x-axis rather than V1, the supply voltage, which we had before, we can just plot the voltage across the diode only, because that node relative to ground, well, the only component in between the two is the diode. So we're measuring at VN002, we're essentially measuring the voltage across the diode. So back to our schematic for the last time. Down at the bottom here, when you hover your cursor over the x-axis, you'll see this sort of ruler symbol that appears. And if we right-click on that x-axis, you'll see that the plotted quantity is V1, and V1 was our supply voltage. I'm going to change that to VN002, 002, which was in brackets. And when we click OK, we've changed now our graph to reflect just the voltage across the diode, and up the side is our current as before. And so now hopefully we recognize the diode characteristic more readily. What I'll do is I'll get rid of this power curve here. I'm going to do the same as before. If you remember, it was function F5 to delete. We can delete a trace by just hovering over its title there, and we can get rid of it. And I'll press escape so that I don't accidentally delete anything else. Okay, so here we've just got our current curve as the voltage across the diode increases. And what we know from sort of semiconductor theory is that as the voltage increases across the diode, we see very little current at all until we reach a point which is termed the activation voltage. And at this point here, we know that for the PN junction, the depletion region breaks down and current is allowed to flow. And we see this sort of big increase on our graph at that activation voltage there. Again, same as before, we can, if we want to, take specific measurements for particular currents and particular voltages by choosing a cursor there. By clicking once, we can drag that along and back to see corresponding voltage and current readings at different points on the graph. So I hope this video was useful, first of all, as an introduction to LT Spice, which can be a little bit daunting, especially if you're a Mac user. But then secondly, to see how we can use LT Spice to produce a very simple circuit and see a diode characteristic.